You've probably already heard of at least the shortcut version of Newton's third law of motion. And the way that goes is for every action, there's an equal and opposite reaction. Sometimes it's just called the law of action-reaction. And the problem with stating it that way is it's a little bit vague. What's the action and what's the reaction? And to give you an example of that, imagine an action in which somebody hits somebody in the face. So the action is, let's say I punch some guy in the face. So what then is the reaction to that? Here's where it's a little unclear. Because if I hit somebody in the face, maybe the reaction is, okay, he hits me back. I probably deserve that. Or maybe the reaction is he just cries. Or maybe the reaction is he calls the police. Or maybe he calls his lawyer. It's not clear when you just say action, reaction. So to make it a little bit more clear, let's state it a little bit more clearly. Let's state it like this. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Now that's a lot wordier, but if we apply it to the previous example, you'll see it's much more clear. We get a really clear picture of what the reaction is. So whenever one object, let's say the one object is my fist, exerts a force on a second object, let's say that's his face, the second object, well that was his face, exerts an equal and opposite force on the first. That was my fist. So here it is, really, really clear. No vagueness whatsoever. If I punch somebody in the face, well, maybe they cry, maybe they hit me back, maybe they call the police. But what will definitely happen every time is their face will hit my fist with exactly the same force. And this is why if you hit somebody in the face, your hand could really hurt. You could even break a finger. In fact, if you're like me, when you were in elementary school and you were kind of a nerd, if you ever got beat up, you could always come in the next day and say, hey man, you couldn't believe the way I hit his fist with my face. And it's absolutely true. So now that we're clear on what's action and what's reaction, let's go about trying to really understand this law and making sense out of it. And I think a good way to do that is to take a look at a couple of videos I have here for you. So let me tell you what's going on in this first video. You see two cars. Here's a car on the left and here's a car on the right. And they have the same mass as each other. I mean, they're identical. Let's say maybe this one is 1 kilogram, that one's 1 kilogram. Right now they're at rest. In between them is a compressed spring, and I'm about to hit a trigger that will cause that spring to push apart. And that'll cause the two cars to push on one another. So according to our law says whenever the car on the left exerts a force on the car on the right, that the car on the right will exert an equal and opposite force on the car on the left. So these two forces should be identical to one another. Let's watch the video and see if that's what it looks like. There you go. So you can see that when I hit the trigger, those two cars pushed away from one another. And from what it looked like, they had exactly the same speed as one another. So I don't think it's hard to believe at all in this video that they exerted exactly the same force on one another. They had the same mass, and they ended up with the same speed after the push. That one's not too hard to understand. Let's take a look at the next video that'll be a little bit more of a challenge to understand. And here we go. All right, in this video, the difference is that now the car on the right has a large mass on top of it. In fact, now this car is about 3 kilograms. Whereas this car is still only about 1 kilogram. And again, even though they have different masses, according to Newton's third law, whenever the car on the left exerts a force on the car on the car on the right has to exert an equal and opposite force on the car on the left. So when they push off one another, those two forces, according to the law, have to be equal and opposite to one another. Let's see what happens. All right. So that didn't look equal and opposite. this car is moving relatively slowly, and this car is moving really fast. And this is where it becomes a challenge to really understand Newton's third law. But I think with just a little bit of explanation, it'll make sense to you. So let's put a number on these forces. Let's say that Newton's third law is true, and let's say that they exert a force of 9 newtons on one another. So they're each feeling a force of exactly 9 newtons. So why don't they have an equal reaction? Why does this car go so fast and this car hardly moves at all? How could they possibly be exerting the same force on one another when this one goes slowly and this one goes so quickly? Well, if you're watching the video on Newton's third law, hopefully that means that you've already learned Newton's second law, which is really a formula that says that an object's acceleration is based on how much total force is acting on it. The more force, the more acceleration, divided by how much mass it has. The more massive something is, the harder it is to accelerate. So it's on the bottom of the equation. So if we calculate what we would expect the acceleration to be of the car on the left, if the force is 9 newtons and that car has a mass of 1 kilogram, we would expect an acceleration of 9 meters per second squared during the push. What about the car on the right? Well, if the force is identical, 9 newtons, but the mass is 3 kilograms, 9 divided by 3 is only 3 meters per second squared. And so we should expect, even though they're feeling exactly the same force, that the car on the right doesn't have anywhere near as much acceleration. And that's exactly what happens in the video. See, I think the problem with Newton's third law is that people are distracted by motion. There's a lot of motion over here. And so the assumption is the car with a lot of motion, that's the car that's experiencing the most force. But what people forget about is mass, that it takes a lot more force to give the same speed to something that has a lot of mass. Or another way to say that is something that has more mass simply isn't going to accelerate as much, even though the same exact force is acting on it. So hopefully you can start to believe that in this seemingly unequal situation, large mass and small mass, they really do exert the same force on one another. So let's see how well we really understand this law by applying it to the most unequal situation we can think of. So you can see what I have here on the screen. Imagine that we have a high-speed locomotive train, and some poor little kid left his tricycle on the train tracks. So these are two objects are very, very different from one another. A huge, fast-moving, let's say it's going 100 miles an hour train, and a tricycle sitting at rest on the train tracks. According to Newton's third law, whenever the train exerts a force on the tricycle is going to exert an equal and opposite force on the train. How can that be possible? Because we know what's going to happen here. When the 100-mile-an-hour train hits the tricycle at rest, that tricycle is going to go flying. I mean, it is going to go hundreds and hundreds and hundreds of feet into the air and land far, far away from the point of impact. Meanwhile, what's going to happen to the train? Well, if you're back here sitting on the train, you are barely going to notice. You might feel a little tiny bump, and that's it. So how could they be exerting exactly the same force on one another? The tricycle goes flying, and you barely feel anything. Think about the answer. Do you have it? Well, the answer is mass. Think about what a small mass the tricycle has and what a huge mass the train has. If they're feeling exactly the same force, that force divided by a huge mass is going to give you a very small acceleration for the train. That exact same force divided by a small mass is going to give you a large acceleration for the tricycle. So no surprise that it goes flying. The other thing to think about is, why does the tricycle get crumpled up so much and the train barely has a dent on it if they're exactly the same force? Well, think about what a tricycle is made out of. Probably cheap aluminum. It doesn't take a whole lot of force to crumple up cheap aluminum. That exact same amount of force on the thick steel that the front of a train is made out of is barely going to make a dent. So hopefully, now that you have had a chance to really think about it, Newton's third law makes sense. That whenever one object exerts a force on a second object, the second object really does exert an equal and opposite force on the first.